Hello, welcome everyone. In today's lecture, we are going to be using Castigliano's method again, but then we are going to look at a slightly more complex structure. So most of the examples that you have looked at are essentially either simply supported beams or cantilever beams, where there's only one segment that you have to look at. Now we look at a more complex structure and also look at a case where we have not one force, but two forces acting at the same point. Okay, so this problem is going to be somewhat lengthy, so I want to make sure that I take you along the whole way. Okay. So by the end of the lecture, what you will be able to do is that you will be able to analyze the deflections of complex beams that are subjected to multiple forces and which experience more than one type of deformation. So if you look at all the examples that you've done so far, we essentially have had only bending deformation. So in this particular lecture, you look at a case where there's both bending deformation as well as axial deformation. In the homework that is associated with this particular lecture, you will look at a case where you have bending and torsion. And if you're able to solve both these types of problems, you can essentially look at any structure that is subjected to bending, torsion, and axial deformation, and at any configuration, and use Castigliano's method to find both the deflection as well as the rotation. Okay? So let's look at the example at hand. Okay. So here is the structure. I want to kind of go through this a little bit carefully. So essentially, the structure lies in the XZ plane. Okay, so segment AB and segment CD, they are parallel to the x-axis, and the segment BC is parallel to the z-axis. So this entire structure is lying in the XZ plane, and you have two forces, Fz and Fx, equal to 100 pounds and 150 pounds, that is acting at point D. Okay. The lengths of each of these segments is given. It is 6 inches, 5 inches, and 2 inches. And it's also given that the moment of inertia, the Young's modulus, the area, the shear modulus, and the polar moment of inertia are all same for all these segments AB, BC, and CD. So essentially, only the lengths of these segments vary. The cross sections are identical. Okay. And in this case, we are asked to find out what is the deflection of this particular structure at point D in the x direction. Okay, so there are multiple things that you need to be careful about here. Again, we are looking at the deflection at a specific point in a specific direction. Okay, so essentially, we have to take the derivative of the strain energy with respect to the force that is being applied at that point in that particular direction. Okay, so in this case, you have an Fx already acting at point D, so you have to take del u by del Fx. So even though Fx is a given force, we still have to assume that it is actually a variable force. Okay? The Fz value is also given, so you can either treat Fz to be 100 pounds or a variable. The only advantage is that if you take it as a variable, then if you want to find the deflection at point D in the z direction, all you have to do is take the derivative of the strain energy with respect to Fz. Okay, so it actually makes sense to have both Fx and Fz as variables. Okay, so let's go ahead and see how we go about solving this problem. Okay, we know that based on Castigliano's second theorem, the deflection in the x direction at D, delta x, is del u over del Fx. Okay. Now, what is going to be del u in this case? Right? Del u in this case potentially could be composed of the axial strain energy, bending strain energy, and the torsional strain energy. Okay, so that is the most general case. Okay, and you have contributions to all these three components in all the three segments potentially. So you can have bending in AB, you can have torsion in AB, or you can have bending and torsion in BC, or axial deformation and torsion in CD. So we have to worry about all these different types of deformation modes in all the segments. So essentially, we have to find the contribution to strain energy in all these segments due to all these deformation modes and use that to calculate the total strain energy in the structure. Okay, so that is something that you must keep in mind. In this case, though, we are a little bit lucky because the two forces Fx and Fz act on the plane of the structure. Okay, therefore, you are not going to have any torsional deformation. If you, on the other hand, had a force in the y direction, you would also have the torsional deformation of the structure. So in this case, we are lucky. So we are going to have just bending deformation and axial deformation. Okay, but we still have to consider both of them for all three segments. So we are going to look at each segment, one segment at a time, and find out what is the axial deformation and what is the bending deformation in each of the segments, and calculate the appropriate strain energy in each segment, and then add them all up. Okay. So let's first look at the segment CD. Okay. So what I have done is I have taken a cut between this point C and point D. Okay. And I'm looking at the free body diagram. Okay. So if you look at the free body diagram, you have these two forces Fx and Fz that is acting at the tip at point D. So you are going to have three internal reactions. You are going to have an internal normal force, PCD. You are going to have an internal shear force, VCD. And you are also going to have a bending moment, My. Okay. Now, in this class, we ignore the effect of the shear stress or the shear force, VCD. So even though it can also contribute to the strain energy, we usually ignore that in this class. So we essentially have to worry about only the strain energy that comes from PCD and My. Okay? When I say PCD, it means the internal axial force at any point between C and D. So similarly, when I say MYCD, it essentially means the internal moment along the y direction at any point between C and D. These things can be either constants or be variables. Okay. Now, the other thing that I also done is that even though we have a coordinate system for the entire problem, which is given, this is the coordinate systems x, y, z, but in some cases, it is useful to define a local coordinate. Okay, and that is what I have done here. This x bar is a local coordinate that starts at point D and ends at point C. So x bar is going to vary from 0 to 2 since the length of the segment CD is 2 inches. Okay, so what I am going to do is I am going to write both this PCD and MYCD as a function of x bar. Okay, and then I am going to find the strain energy by integrating for x bar starting from 0 and ending at 2. Okay, so in this case, it's actually very simple. The internal normal force is just going to be equal to Fx, okay? Because Fx plus Fx should be exactly equal to PCD because they're in the opposite directions. And similarly, Fz will be equal to VCD, but we don't worry about that. And we can also find out what MYCD is. Okay, I want to tell you something very important here. This MYCD is because the y direction is the vertical direction. Okay, so when you apply a force like this on the structure, it will have a tendency to rotate the structure in that manner. Okay, which means that the moment reaction at any point between C and D is going to be in the opposite direction, that way. Okay, so that is the reason why the bending moment is going to be, sorry, I made a mistake there. So the direction of rotation of Fz is going to be like this. And to counter that, the moment at any point between C and D should be in the opposite direction. So one is trying to rotate it clockwise, the other is trying to rotate it counterclockwise. So now if you use your right hand rule and then curl your fingers along this blue curve, then your thumb will be pointing up. Okay, so the moment is along the y direction. That is why we have this My CD, and that is going to be nothing but this Fz times this x bar. Okay, so that is how you get this expression for MYCD. Okay, so that is something that you must keep in mind. So you always have to be careful about finding out what is the direction of the moment that is going to be happening internally and have the right sign and the right subscript. Okay, so in this case, it's a moment in the y direction, and that is a bending moment, and that turns out to be Fz times x bar. Okay, now once you know PCD and MYCD, it's actually very trivial to find out what the internal energy in the segment UCD is. So essentially, you take integral 0 to L of p squared dx by 2ae plus the integral 0 to L of m squared dx by 2ei. Okay, and that is what I have done here. So the first term is the internal energy or the strain energy due to axial deformation, and the second term is the internal energy due to bending. Okay, and then I'm just substituting the values of PCD and MY we just derived. Okay, so that is how we get UCD. The exact same procedure applies for the segment BC. Okay, so this is the overall structure. I just put it back so that you kind of keep track of what is going on. But then this is the free body diagram for the segment between B and C. So here again, I'm taking a section between B and C, and I'm looking at the free body diagram of that structure. So I'm essentially taking this whole segment there. Okay, and that is how the free body diagram looks like. So again, we are going to have an internal shear that we are going to ignore. We are going to just worry about the internal axial force and the internal bending moment. Okay, so in this case again, the bending moment is BC, and this force here, PBC, I have taken PBC to be in this direction. So PBC is going to be minus FC, because FZ plus PBC will be equal to 0 for force equilibrium to be satisfied, which means that PBC is going to be equal to minus FC. Now, the My function for any point between B and C is a little bit more complicated, because you are going to have a bending moment due to both Fx as well as Fz. Okay, the bending moment bending moment due to Fc at any point between B and C is going to be a constant. Okay, it just depends on this arm length of CD, which is 2 inches. So one contribution to the bending moment comes from Fz, and that is nothing but Fz times 2 inches. On the other hand, the bending moment contribution due to Fx is going to depend on the distance of this point from this point C. How far that point is from point C will determine what is the bending moment due to Fx's. So that is why the second term is Fx times x bar. So there is 2 contributions to the bending moment from Fc and Fx. One is a constant for any point between B and C. The other is a variable. Okay, but again, it is not very difficult to write a bending moment function like this. But then once you do that, it's the exact same process. You take the integral from 0 to 5 of p squared dx by 2ae plus the integral from 0 to 5 of m squared dx by 2ea. You have the limits from 0 to 5 because the length of the segment BC is 5 inches. Okay, so you start at x bar equal to 0 and you go until x bar equal to 5 inches. Okay, so again, this is a local coordinate that we are using, and we sometimes use these local coordinates because it makes it easier to write the moment functions and the internal torque functions and so on. Okay, so essentially these local coordinates are often used because they make the algebra a little bit simpler. Okay, so we have done this for segment segment CD and segment BC. Now we are going to do the same thing for segment AB. Okay, so for segment AB, this is going to be the free body diagram. Okay, again, we are going to ignore the shear force. We are going to worry about only the axial force and the bending moment. Okay, the axial force in this case, again, very trivial. PAB is just going to be equal to Fx. The bending moment along the y direction, it is going to be a little bit more complicated. Okay, so again, there is going to be a contribution due to Fz and Fx. Okay, in this case though, the contribution due to Fx is going to be a constant for any point between B and A. Okay, but the contribution due to Fz is going to be changing. Okay, so this is exactly opposite of what we found in segment BC. There the contribution due to Fx was variable and the contribution due to Fz was constant. Here the contribution due to Fz is varying with respect to x bar, whereas the contribution due to Fx is a constant. Again, we are using a local coordinate, which is x bar, that starts from point B and goes all the way to point A. Okay, but the procedure is exactly the same. Once you know what the internal axial force is, you know what the internal bending moment is, you just substitute that into the expression for the internal strain energy. So this is again the axial deformation term, and that is the bending term. Okay, and here we don't have to worry about the torsional term because there is no internal torque in any of the segments. Okay, now once we have done all these things, we have found out what the internal energy in the segment AB, BC, and CDR, we just put them together. Okay, that is what I have done here. Okay, and now once you know u, you take the derivative of u with respect to fx, and that essentially is going to give you delta x at d. Okay. Now, if you look at these terms, there are lots of terms. There are actually 6 integrals that you have to consider. Okay, and taking the derivative of each one of them is not very difficult, but it could be time consuming. So we can look at a few tricks here. Okay, so one of the tricks that you can use is that we are taking the derivative with respect to fx, right? So if you're taking the derivative with respect to fx, you can essentially ignore any term that doesn't have an fx in it. So if you look at this particular term here, for example, the axial energy term in UBC, it doesn't have an fx term in it. So if you're going to take the derivative of this integral with respect to fx, it's going to be equal to 0, right? So you don't have to worry about that. Okay? The same thing is true for this term here in segment CD, right? It has only an fz term. So if you take a derivative with respect to fx, it's of course going to be equal to 0. So even though we have 6 terms in the internal energy or the strain energy, there are only 4 terms that are essentially going to contribute to the deflection at point D in the direction x. If it is in the direction z, it might be different. Okay, that's something you must be careful about. Okay, so that essentially makes the algebra a little bit simpler. So effectively, you have this first term here, the second term here, third term here, and fourth term here. So essentially, you have to only take the derivative with respect to these 4 terms. Okay. The other thing that you realize is that when you had only one type of deformation, it was a little bit simpler. So essentially, you had only u bending. In that case, the internal energy or the strain energy is, okay, that is just, so you just had to take the integral from 0 to L of m squared dx over 2ei. And then when you take del ub over del p, for example, then it's actually very simple. It's the integral from 0 to L of m by ei, times del m by del p dx. Okay, so it's actually quite simple, right? So essentially you can just use this to evaluate your delta b or delta d, for example, right? But in this case though, it is not going to be that simple because you have contribution from both bending moment as well as axial deformation. So essentially, we have to take the derivative for each one of these terms here that I just mentioned separately with respect to fx. Okay, that is something that you must keep in mind. Okay. Anyway, so it's again not very difficult. It's just a lot of algebra. So that I have already done here. Okay, so you put in all the terms, expand it out, and then you take the derivatives. Again, these are not very difficult. Eventually, if you do all these things, you end up with an expression like this. So that is your delta x at d. Okay, so it turns out to be a kind of a messy expression. It contains a lot of things, but then you can simplify it a little bit more. And if you end up, finally, that is the expression. Okay, so at this point, you can substitute that your fx is actually 150 pounds and your fz is 100 pounds into this expression, and then that will give you your delta x in terms of all the other variables, a, e, I, and g, and so on if you need to. Okay, so that's the process for analyzing a complex beam. Okay, so essentially you have to look at every segment individually, and you look at all the potential contributions to strain energy in all these segments. It could be bending, torsion, and axial deformation. So you have to find the total strain energy, including all these terms, and then take the derivative with respect to a force or a moment, depending on whether you want to find the deflection or a rotation. Okay. Now, one thing that you see in this particular expression here is that you have this expression here that is 8fx over a. Okay. That simply comes from the extension of the segments AB, BC, and CD. Okay. So if you think about delta x due to an axial deformation, that delta is some PL over AE. Okay? So that is this term that you see here. And that depends only on this force P, which is Fx. Okay? And actually you can also see where this 8 comes from. That comes from 6 plus 2. That is where the term 8L over 8Fx over AE comes from. Okay? So length is essentially 6 plus 2, 8 inches. The force is Fx in the x direction divided by AE. That is essentially the axial term. But if you look at the second term, it's a lot more complicated. Okay? You have some really weird numbers like 1150 by 3 and 350. And you have 1 over 2EA outside. Where is all this thing coming from? Okay? This is coming from the fact that you are going to have bending in all three segments, AB, BC, and CD, due to both Fx and Fz. It may not be contributing, both the forces may not be contributing in all particular segments, but they are contributing, right? And when you have bending, things become complicated because you are going to have a deflection due to bending itself, but then when you have bending, you're also going to have rotations, okay? And that rotations are essentially going to cause rigid body motions, okay? And that rigid body motion will also contribute to a displacement, okay? So you might think that, okay, the displacement in the x direction should be dependent only on Fx. No, it also depends on Fz, as this term clearly shows. Because what is going to happen is that this Fz, if you look at this segment BC, for example, okay, just look at a simple case, okay? And then you apply a force Fz here. What is going to happen? This beam BC is going to bend like that, okay? And it is going to bend like this. So if you look at that, this deflection in bending is actually in the x direction. That is why the bending due to Fz also contributes to the deflection in the x direction, okay? And similarly, if you have an Fz here, if you have this AB, that is also going to rotate like that. And if it rotates like that, then the second part, BC, is going to go like that. And since that deflection is in the x direction again, the deflection or the bending of AB also contributes to the deflection at point D in the x direction. So if you think about it, the segment AB is being bent by Fz, but it contributes the deflection in the x direction at point D. Okay? So if you try to look at how the deformations are happening individually and try to figure out what is going to be the deflection at B, it is going to be extremely complicated. So if you try to use the methods that you learned in your solid mechanics class or mechanics of materials class, and then try to find out the deflection and rotations in each segment and somehow add them up algebraically, you will essentially lose your mind. Okay? So it is in these cases where you have complicated structures and multiple forces acting on a particular structure where the Castigliano method is most powerful. So even though it might look tedious in terms of the algebra, the method is actually very simple. Okay? You don't have to keep track of every type of deformation, every type of rotation happening in every segment. You take the internal energy or the strain energy, take the derivative, and you're going to get the deflection. Okay? So you will have a problem like this, maybe not as complicated in your homework, where you'll also have torsion and bending. Okay? And you will see that Castigliano's method is actually very powerful in reducing the complexity of those structures as well. Okay? With that, I'll conclude and see you in the next class. Thank you.